Hi friends, this video is meant for the residue of f of z. How to find the residue of f of z at each of its poles. The formula for residue of f of z at a simple pole. Simple pole means order is 1, z equal to a is residue of f of z at z is equal to a is equal to limit z tends to a z minus a into f of z. So the corresponding term z minus a into the function f of z. Clear? And the second one is the another kind of way to calculate the residue. Suppose the limiting case is not possible. Let us see that the given f of z is equal to g of z by h of z if g of a is not equal to 0 but h of a equal to 0, then the residue of f of z at the point z equal to a is limit z tends to a f of z, that is here the denominator is h of z, the numerator is g of z. So in this formula it is actually g of z, not f. G of z divided by d by dz of h of z. It means that differentiate one time with respect to z, only the denominator, then apply the limit. So this is the second way of getting the residue if it is the special case. And third type is, suppose the pole is of order n, more than 1, like 2, 3, 4, etc., etc. Then the formula is residue of f of z at the pole z is equal to a with the order n, with the order n is equal to limit z tends to a 1 by n minus 1 factorial d power n minus 1 by dz power n minus 1. What's the meaning of this one? Suppose the order is n, we differentiate n minus 1 times with respect to z of the term z minus a whole power n into f of z. So this is actually the general formula to estimate the residue value. Suppose when I substitute n equal to 1, this will give the first formula, isn't it? N equal to 1, 1 minus 1 is 0 factorial, this 1. So no need to differentiate, and n equal to 1. So this will give the exactly the first formula, right? Actually, apart from this, one more technique is there. The technique is with the help of Lorentz series expansion. Yeah, that is the another technique. It is very rare cases, unless otherwise the function f of z is polynomial. So if it is a polynomial functions, we can easily apply these cases. Suppose other than the polynomial, even sometimes trigonometric, logarithmic it involves, then better we can try to expand the given function as Lorentz series expansion, and the residue of f of z at the pole z equal to a of order 1 is the coefficient of 1 by z in the Lorentz series expansion. What is 1 by z? Is mean the principal part. Okay, so when we say that the point is a pole, if you remember, in the Lorentz series expansion of f of z at z equal to a, the principal part contains only finite number of terms. Then only we say it is a pole. So we only pick the coefficient of 1 by z in the Lorentz series expansion. That is actually the residue of f of z at the simple pole z equal to a. Okay. Now let us see a few problems with the help of these result 1, 2 and 3. This exercise let us see later. Answer is also given to you. Please try this one after the first problem. Okay, let us see the first one. Find the residue for the following at each poles. The first question, z plus 2 by z minus 2 into z plus 1 whole square. Hence, the denominator equal to 0 are the poles. So, the poles of f of z are the denominator equal to 0, that is z minus 2 into z plus 1 whole square equal to 0. So, by that way we get z equal to 2 of order 1 is called simple pole, z equal to minus 1 of order 2 is called double pole. Now, let us see how to find the residue of f of z at z equal to 2. So, it is a simple pole. So, by the formula number 1, limit z tends to 2 z minus 2 into f of z. So after cancelling the corresponding terms of the pole z minus 2, substitute the limit value as z equal to 2, 2 plus 2 4 divided by 2 plus 1 3, 3 square is 9. So 4 by 9 is the answer. So what we require residue of the pole at the pole z equal to 2. So the corresponding term get cancelled first. We cannot retain this term because when we retain this one, this becomes infinity. Got it? Then this becomes 0. So we obviously get 0 into infinity is 0. So first cancel the corresponding poles, then we move on to the limiting case. Now the second pole is minus 1 of order 2. So this time I apply the general formula in the place of n equal to 2. So 1 by 2 minus 1 factorial d by dz of power 1. That means only one time. So order is 2 means one time differentiation. Right? So then this is z minus a, that is here a equal to minus 1. So z minus of minus plus 1 whole square. So z plus 1 whole square, z plus 1 whole square get cancelled. Got it? Isn't it? Z plus 1 and z plus 1 they could cancel. Then the remaining is z plus 2 by z minus 2. Now substitute z is equal to minus 1, we get minus 1 plus 2 is plus 1, minus 1 minus 2 is minus 3. So the answer is, I think so, it is 1 by, what is it? This is 1 by coming, no? Yes, it's differentiate, no? We first differentiate z plus 2 by z minus 2 by using u by v formula, then use the limit. The answer is minus 4 by 9. So here we get the first problem. One is simple pole and the other is double pole. Double pole would differentiate after cancellation of this term. That is the idea. Now see the second one. Here my function f of z is cot z. See that cot. Cot is nothing but cos z by sin z. So this is here some special type. G of z by h of z. When sin z equal to 0, the pole is z equal to 0. Actually z equal to 0, pi, 2 pi, 3 pi, 4 pi, etc. etc. Maybe it is n pi. So n pi is also correct. Okay. So here if we choose z equal to 0, what the formula says that once the formula looks like this format, differentiate the denominator with respect to z, then apply the limit. Now here my h of z is sin z. What's the sin z differentiation? Cos z. So cos z will get cancelled. So no z term. So the answer is obviously 1. So for any pole, either you can take 0 or n pi or 2 pi, 3 pi, 4 pi, etc. Because ultimately the denominator and numerators are same. After cancellation of this one, there is no z at all. So the answer is 1. Clear? So the third one, find the residue at the pole z equal to 0 of 1 plus e power z by z cos z plus sin z. So here z equal to 0 is clearly given. So I would like to once again differentiate the denominator with respect to z. We get this uv formula. So u is z, v is cos z. So uv dash, isn't it? uv dash plus vu dash, the first term. So u is z, v is cos z. Cos z differentiation is minus sin z. So minus z sin z plus v. V is cos z. U is z. Z with respect to z is 1. So it is simply cos z. And sin z differentiation is cos z. So totally there are 2 cos z minus z sin z. Now apply the limit. E power 0 is 1. 1 plus 1 is 2. Denominator is z equal to 0. So the second term is completely 0. First term is cos 0 is 1. 1 into 2, 2. So 2 by 2 is answer is 1. Got it? Now with the help of this residue of f of z at each of its poles, we established one theorem. It is called Cauchy's residue theorem. Cauchy's residue theorem. We have started this complex integration with the help of Cauchy's fundamental theorem. Cauchy's fundamental theorem is meant for simple closed curve. With the help of the simple closed curve, we derive Cauchy's integral formula. Even sometimes when we use the Cauchy's integral formula for derivatives, suppose the singular points are having more than order 1. Here there is no such confusion. Very simple. Cauchy's residue theorem with the help of residue. So that's why it is named as residue theorem. So already we know how to find the residues of f of z at each of its poles. Clear? Let us see the statement of the theorem. If a single valued function f of z is analytic inside a simple closed curve C except for a finite number of isolated singular points, is also known as poles. Okay, like a1, a2, etc. an inside the C, then integral over C f of z dz is equal to 2 pi I into sum of the residues of f of z at each of the singular points a1, a2, etc. am. Right? So this is 2 pi I into sum of the residues. 2 pi I into sum of the residues. What is C? C is the simple closed curve. Now before start with the application of the Cauchy's residue theorem, I want to say that this is nothing but the Cauchy's fundamental theorem for multiply closed curves. If you remember, if f of z is analytic inside a simple closed curve C containing a finite number of simple closed curves, namely C1, C2, etc. Cn, then integral over C f of z dz is equal to integral over C1 plus integral over C2 plus etc. etc. integral over Cn f of z dz. So what about integral over C1 f of z dz is nothing but 2 pi I into residue of f of z over the curve C1. There is only one isolated single point A1. For the second circle we have A2. So in generally for the mth term we get the AM. So that is the way we are getting this Cauchy's residue theorem with the help of Cauchy's fundamental theorem for multiply closed curves. And very important concept here, these points are lies inside. Suppose the point lies outside, then the residue of f of z at the pole is 0. Suppose the point or the pole z equal to a lies outside the given circle C or simple closed curve C, then the residue of f of z at z is equal to a is 0. Yeah, this is the important note. Got it? Lies inside, apply the formula to find their residual value. Outside means no need to apply any formula, simply 0. Let us see the first question. Evaluate integral over c 2z minus 1 by z into z plus 1 into z minus 3, where c is mod z equal to 2 by using Cauchy's residue theorem. You see this term specifically mentioned by using Cauchy's residue theorem. Suppose this is not given, we can do the same problem by Cauchy's integral formula. But before going to that, what are the poles of this function f of z? 0, minus 1, plus 3. Got it? So the poles of f of z are the denominator function 0 order 1, minus 1 order 1, 3 is also order 1. So all are 3 are simple poles. Now first check whether these points are lies inside the given circle mod z equal to 2. What it means that the circle whose center is the origin, the radius is 2. Now let us substitute in the place of z is equal to the points 1 by 1. First point is 0, so 0 less than 2, so it lies inside. Substitute the minus 1, mod minus 1 is plus 1, it is also less than the radius 2, so lies inside. The third point is 3, mod 3 is 3, it is greater than 2, sorry, this is lies outside. So what about the residue of f of z at this pole z equal to 3? It is simply 0 because it is lies outside. 0 and minus 1 is lies inside. So find the residue only for these two poles, and finally adding up all the residual value into 2 pi I. That is the required answer. So find out the first one. Residue of f of z at z equal to 0 is equal to limit z tends to 0, z minus 0 into f of z. Z get cancelled. Substitute z equal to 0 in the rest of the part. We get minus 1. Here 1 into minus 3 is minus 3. So minus 1 by minus 3 is plus 1 by 3. So this is the residue of f of z at the first pole z equal to 0. Now what about the pole z equal to minus 1? Let us see. Residue of f of z at z equal to minus 1 is limit z tends to minus 1, z minus of minus 1 into f of z. So the corresponding term get cancelled, right? The remaining is 2z minus 1 by z into z minus 3. Now apply the limit z is equal to minus 1, minus 2 minus 1 is minus 3. Here minus 1 into minus 3 minus 1 is minus 4, minus of minus plus 4, so minus 3 by 4. So I found all the residual values. So by Cauchy's residue theorem, integral over c 2z minus 1 by z into z plus 1 into z minus 3 dz is equal to 2 pi I into the sum of the residues of f of z at the pole 0, minus 1 and 3. This is outside, so it is simply 0. So this is the inside, so we found this value 1 by 3. This is minus 3 by 4. This is outside, so 0. So to simplify this, we get the answer is minus 5 pi I by 6. Got it? So this is the application of the Cauchy's residue theorem. Comparatively, Cauchy's residue theorem is easier than the Cauchy's integral formula. Why? Let us see. Suppose this is the question given. If I want to apply the Cauchy's integral formula, I want to apply the method of partial fraction first, like z plus 1, z minus 3. Then among the 3, this is outside. Then we apply the formula. But here there is no confusion. Just simply check the points are lies inside or outside. Outside means residual is 0. Inside means find those corresponding residual value. And by using Cauchy's residue theorem, 2 pi n is sum of the residues. That's it. No need to apply the method of partial fraction. Nothing. Right? So suppose in the question paper, the question is evaluate, doesn't mention the name of the theorem or formula. I strongly recommend you to apply the Cauchy's residue theorem. Got it? Some more problems in the Cauchy's residue theorem. Question number 1. Integral over c e power z by z plus 1 whole square dz, where c is mod z minus 1 equal to 3. So circle with the center is 1, radius is 3. What about the pole? The pole is minus 1 of order 2. Correct, sir? Now substitute the place of z equal to minus 1. We get minus 1 is minus 2 only. Modulus of minus 1 is plus 2. 2 is strictly less than 3. So this pole lies inside. So find the residual of f of z at the pole z is equal to minus 1. See, this is the order 2. So by using the formula 1 by n minus 1 factorial, there is 2 minus 1 factorial is 1 factorial. One time differentiate. Okay, z plus 1 whole square into f of z. After cancellation of z plus 1 whole square, e power z. E power z once again with respect to z is e power z. Now substitute z equal to minus 1, we get e power minus 1. So by Cauchy's residue theorem, we get is 2 pi a into residue of f of z at the pole minus 1. That is e power minus 1. So we get the answer 2 pi I e by e. So that is the answer. Got it? So this is the simple way to evaluate the given integrals by using the Cauchy's residue theorem. Similarly, the second one we already did, integral over c 2z minus 1 by z into z plus 1 to z minus 3. Yeah, we did this already. Move to the other sums. Yeah, let us see the third one. Integral over c z minus 1 by z plus 1 whole square into z minus 2, where c is mod z minus I is equal to 2. So let it be the whole is f of z. The poles are nothing but minus 1 of order 2 and plus 2 of order 1. Clear? Right? Now check whether it lies inside or outside. Yeah, let us see that. If I substitute z is equal to minus 1 in the given c, what is c here? The c is mod z minus 1, I is equal to 2. Substitute z equal to minus 1, we get mod minus 1 minus I is nothing but square root of minus 1 whole squared plus the coefficient of I minus 1 whole squared. So root of 2 value is I think 1.414. Root 2 value is 1.4124. It is less than 2, not this one, it's 2 actually, since radius is 2 only, no, so it is lies inside. When I substitute z is equal to 2 here, we get mod 2 minus I. What is 2 minus I means? Square root of 2 squared is 4. The coefficient of I is minus 1. So minus 1 whole square is 1. So 4 plus 1 is root 5. Root 5 is I think 2.236. So it is greater than 2. So this lies outside. So once it is lies outside, the residue of f of z at z is equal to 2 is 0. Clear? Now find out the residue of f of z at z equal to minus 1. So limit z tends to minus 1 dz by z. Because of order 2. So one time differentiation. To cancel this one, we get z minus 1 by z minus 2 using u by v formula. I think so. I have explained here the adjacent to that. Using u by v formula, what is that? This is v z minus 2 whole squared, v z minus 2 u dash 1 minus u is z minus 1 and v dash is 1. Let us simplify this. I think z minus 2 minus z plus 1. So z get cancelled. Minus 2 plus 1 is minus 1 by z minus 1 whole squared. Now substitute z is equal to minus 1. We get minus 1 minus 2 minus 3 whole square is plus 9. But in the numerator we have minus 1. So the answer is minus 1 by 9. So by the Cauchy's residue theorem, 2 pi I into the sum of the residues. So minus 1 by 9. What about the other pole? It is 0. So this is the answer. Understand? This is the answer for the question. Let us see the last example in this Cauchy's integral formula. Integral over c dz by z squared plus 4 whole squared, where c is mod z minus I equal to 2. Okay. What is f of z? So this may f of z. I can split this into two factors, z plus 2i into z minus 2i. Looks like a plus b into a minus b is a squared plus b squared, that is z squared plus 4, because 2I whole square is 2 squared I squared, I squared is minus 1, so we get z squared plus 4 here. So from this, z equal to minus 2I is of order 2, z equal to plus 2I of order 2. Now check whether this lies inside or outside. See that how to check. The given C is mod z minus I is equal to 2. Now substitute minus 2I in the place of z. So mod minus 2I minus I is mod minus 3I. Otherwise it is 3. Isn't it? Minus 3 whole squared under the root. So root under the square get cancelled. So 3 1 is the answer. So it is greater than the radius value. So this lies outside. When I substitute z equal to plus 2, 2I minus I is I. So the answer is 1 is less than 2. So this lies inside. So one pole is lies outside, one pole is lies inside. Clear? For the outside pole, the residual value is 0. Isn't it? Minus 2 is lies outside, so it is 0. For the inside pole, let us see how to find the residue value. Limit z tends to 2I of order 2. So one time differentiation, z minus 2I whole squared into f of z. F of z, I can rewrite 1 by z plus 2I whole squared, z minus 2I whole squared. So the corresponding pole term get cancelled. The remaining is 1 by 2I plus whole squared. Differentiate this one time with respect to z. What is 1 by x differentiation? Minus 1 by x squared. What is 1 by x squared differentiation? Minus 2 by x cube. So here x is z plus 2I. So minus 2 by z plus 2I whole cube. Substitute z is equal to 2I now. We get it is minus 2 divided by 2I plus 2I, 4I whole power 3. That is 4 cube 64, I cube. I cube is minus I. So minus minus get cancelled. 2 by 64 is 1 by 32I. So by using Cauchy's residue theorem is 2 pi I into the sum of the residues. So one is inside, another one is outside. So the inside residual value is 1 by 32I. Outside is 0. So when we substitute this residual value, then simplify this, we get the answer is pi by 16. Got it? So these are the applications by using Cauchy's residue theorem. A few problems for your practice. Please just we can try this question. Okay, see the questions. Integral over c z squared minus 2z by z plus 1 whole squared into z squared plus 4 dz, where c is mod z equal to 3. So these are some problems. Kindly note it down, these problems. You can have the answer as well as here. So let us work out. Thank you.